That's good. That is good. Somewhat. So it seems like, y'all have a pretty good idea about it. So I'm not going to spend too much time on it. Okay. Um, basically, as I wrote up here, hybridization is just a theory of you combine a mixture of atomic orbitals to give rise to some new hybrid orbitals. So we know our atomic orbitals are s orbitals, and we have p orbitals, and typically we have 3p orbitals. So there's a few types of hybrid orbitals. The first one with the most s character is sp hybridized orbitals. And the way to identify whether something is sp hybridized is look how many electron groups it has. So the best one that I can think of off the top of my head is this carbon in this specific molecule. It has 1 and 2 electron regions, right? So even though this is a triple bond, we only count it as 1 electron region when we're talking about hybridization. So it'll be sp, right? So this is going to be an sp, and then so you know that this is an sp hybridized carbon. Same thing with the one on the right. But that is when we take one s orbital and hybridize it with 1 p orbital. If we take an s orbital and hybridize it with 2 p orbitals, we make something called an sp2 hybridized orbital. And that is when, again, you have 3 things connected to an atom. So the best, you're going to see this a lot later down the line, but it is carbons that are sp2 hybridized. So we have here formaldehyde. We count our electron regions. We have 1, 2, 3, s, p, p. So s and 2 p's would give sp2 hybridized. That tells us that that carbon atom, and we're talking about the atom specifically, we're not talking about the overall molecule. The carbon atom is sp2 hybridized. And then the last one is when you take 3p orbitals and 1 s orbital, and you mix them, and you get an sp3 hybridized orbital. There's a couple more actually, and that is going to be the most simplest thing is when you have methane. So CH4. You have 1, 2, 3, 4 electron regions, s, p, 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 sp3 hybridized carbon. There also is situations when you have, let's see, when you have incorporate d orbitals. So we know we have s, and we have 3 p orbitals, and we can hybridize with 2 d orbitals. So if you're in this region where you take 1 s, 3 p's, and 1 d, that would give you an sp3d hybridized orbital. And this is seen with, wait, what was the question, Rich?
Is it charge effective?
No, charge should not affect the hybridization of something. So we have nitrogen here, here, here. This is the so this is going to be nitric acid. This nitrogen has 1, 2, 3 electron regions. Even though it has a positive charge, it is still going to be what hybridization? sp2, right? So we have spp. So sp2 hybridized, so despite having a charge on it. Yeah.
Will they ever ask you like which bond region or electron region is the S and which one's the P, or is it kind of hard?
No, because this is all, it's each orbital or each bond here is comprised of an sp2 hybrid orbital. So there's an sp2 hybrid orbital here, sp2 hybrid orbital here, and an sp2 hybrid orbital here. The hybridization is a characteristic of the atom itself, not a single bond. But we do know that whenever you have a double bond or a triple bond, one of those is going to be a pi bond. I'm sure you didn't learn that yet. So one of these let's say that one is a sigma bond, and that's going to be denoted like that. And that double bond is going to be our pi bond. That sigma bond is going to be sp2 hybridized. This bond here is sp2 hybridized. And this bond here is sp2 hybridized. So the sp2 hybridized is just a characteristic of the atom. But when you add like double bonds, those are not going to be hybrid orbitals. Those are just p orbitals that are overlapping to make a pi bond. If that makes sense.
So the pi orbital, I mean, the pi bond is not an sp2.
It's not. It's a p. It's a pi bond composed of two p orbitals overlap. So we said earlier. Let's look at this one here. Where was it? We said when we take two p orbitals and one s orbital, we make sp2 hybrid orbitals, right? Well, what happened to that other p that we didn't use? So we took one s, two p's. Let me cross out these other ones. We took one s, two p's to make our sp2 hybrid orbitals. Well, we left that other p. This other p orbital is going to be the orbital that's utilized in that pi bond. So that's the whole idea of what's it called? Hybridization. And if we look here, we had used on this one, we used one s orbital and one p. Well, we still have two p orbitals left over, and these p orbitals contribute to the triple bond that we see. So we see two triple bonds because there's two leftover p orbitals. But let's just say, if you don't see it, let's say that these two green ones are going to be our pi bonds. And this red one here is going to be our sigma bond. Well, this is also our sigma bond. So both of those are our sigma bonds. And we know that our sigma bonds for this specific compound have a hybridization of what? Sp. Our sigma bonds are going to be sp hybridized, where our green bonds, the ones involved in the double and triple bond, or I guess this is the triple bond, but the other two bonds right here are going to be our extra p orbitals that we had left over. It's really hard to conceptually understand. All you're going to be asking the question is, what is the hybridization of this carbon atom? Okay. You may ask, you also will be asked how many pi bonds are in this molecule. We know that whether it's so single bonds have one sigma bond, right? That's a orbital sigma. Double bonds have one sigma plus a pi bond. Triple bonds have a sigma bond plus two pi's. So this is what you need to know for this class. Okay. So it's going to ask you, it may give you a complex structure like this, where you have some pi bonds here, and then this one is bonded to an oxygen, which is bonded to something else with a pi bond there. And it may say, let's just imagine these are all filled in. They may say how many pi bonds are in this structure. You're going to get a question like that, and then it may say, it may label these like this, and it may say, what is the hybridization of carbon 2? And it'll be a multiple choice question. You have sp, sp2, sp3, sp3d, and sp3d2. So you'll get a weird looking compound. Don't be alarmed with the compound, or don't be scared of how big the compound is. Just, you're either asked, what's the hybridization, or how many pi and sigma bonds are in this compound? Got it? So if there is no further explanation needed for hybridization, if that makes sense. Yeah, what's up?
So we had a question on this practice exam. It's 12. Do you mind looking?
Yeah.
It's about hybridization.
Into Which atomic orbital involved in causing- And which as lone pair orbitals for H2. Okay. So N2H2 looks like this. I think that should be a double bond in between, right?
Yeah,
Because it looks like it got smudged off a little bit. So the question is, you have this compound N2H2, and it's asking which atomic orbitals are involved in bonding and which as lone pair orbitals for N2H2. So for the bonding orbitals, it's going to be, we're looking at this is a bond and this is a bond. Okay, first, the best thing to do is identify what is the hybridization of the atom involved. How many electron regions are there? 3, which corresponds to spp, sp2. So that's sp2 hybridized on that. And we know that each of these sigma bonds for the nitrogen is composed of an sp2 hybrid orbital. How many sigma bonds are in the double bond? 1. So that's composed of a sp2 hybridized orbital. And we know that our electron pair resides, it must reside in what kind of orbital? It's the same kind, sp2. The only electrons that are not in a hybridized orbital are when you have either a double or triple bond, they're going to be in your p orbitals. And because hydrogen is in the 1s part of the periodic table, it doesn't hybridize because it only has an s orbital. It doesn't have any p orbitals. So we should know that looking at the answer choices, D would be wrong because it says that hydrogen is hybridizing with an sp2 hybrid orbital, but we know that it can only have an s orbital. So knowing that, we can say that the bonds are with a hydrogen s orbital, a nitrogen sp2, and also a nitrogen p orbital, because the p orbital is in here. There's also a sp2 hybridized orbital in here. And the lone pairs reside in, what did we say? sp2. So there's only one. It looks like you got the answer right.
yeah, I was just asking.
There's a key,
What?
there's a key to this review.
Yeah,
Like that.
I'm just saying it looks like you got it right, but I mean, he did get it right.
Or I think he means like, he just circled the right answer.
Oh, you didn't understand why, I see. Yeah, so again, it's because hydrogen can only have, I guess you wouldn't even say hydrogen's hybridized, because it doesn't hybridize, it's just a single s orbital. So it can only have s. I'm gonna try to take a picture of this so y'all can see the question. Camera, so the people on Zoom can't see that. So we're looking at question 12 here. And based on what we drew earlier,
So that P comes from that pi bond from the double bond?
exactly, yeah. All right, yeah, so the P in answer choice B is coming from that pi bond right here. Because we know that double bonds are composed of a sigma bond and a pi bond. So that's where the P is coming from. And the sp2 orbitals for nitrogen are really everywhere. They're one here, and one for that lone pair. And we know, we just said that the lone pair it's in an sp2 hybridized nitrogen orbital.
So the p orbital just comes from pi bonds? Essentially?
The pi bonds come from p orbitals.
Okay,
Yeah,
so if we just see like only sigma, like, for example, like methane, like CH4, even though it's sp3 hybridized, there wouldn't be any p orbitals.
no, because you have no empty p orbitals, because all your
And
p
the same thing
orbitals
with
are
like NH3, right? Still, like, even though it's sp2, it's only,
NH3 is
or it's
sp3.
sp3, but Like,
Yeah.
it would still, none of those bonds, top five bonds, it would still be like.
Yeah. And if it's SP3, automatically it has no pi bonds, because in order to have a pi bond, we need the empty p orbital. And we said you have S, P, P, P. To make SP3 hybridized orbitals, you have to take all those to make SP3, which means you have no empty p's. Whereas when you have SP2, you take those two and the S, leaving you with an empty p.
Like in the case of like HCM, there would be two p orbitals, right?
Yeah,
Okay.
so there would be, this carbon is SP2 hybridized, this nitrogen is also SP, no, SP, not SP2, yeah.
Why is the lone pair SP2?
Because it's going to, is it occupying the,
Why P and two?
where's P energy?
I said and P on N.
Yeah, the P orbital on.
Yes.
Yes, okay, so your question was first, why is the lone pair in SP2? What would you hypothesize that it would be if it's not in an SP2 hybrid orbital? If it's not in an SP2 hybrid orbital, what do you think it would be in? Well, that would change the whole hybridization of the atom. So if we have,
We just found out that certain things have letters on them. One of them, like, if they have four bonds, just subtract one and then.
Yeah, I literally, that's
That's what I've
I've been the entire time.
I mean, if that works,
So like,
But like
when
with.
yeah.
Yeah.
hybridization is the lone pair plus the bond pair.
that's formal charge.
Or, it's the unbonded electron pairs and then like the connection. Yeah. Atoms.
Wait, so what were you, are you just saying you just kind of understood how to identify the hybridization, but not necessarily?
Yeah.
So if we look at something like ammonia, we know that this is what hybridization. SP3, right? Because it has four orbital domain, or not electron domains, right? Which means that these electrons are in an SP orbital, and the way I'm drawing it is literally the way the orbitals look. They're like lobes. This one is an SP3 orbital. This one's in an S3 or SP3 orbital. You can't just leave the lone pair out. The lone pair occupies an SP3 hybrid orbital. It just does, like. What?
It's just like, it's not connected to anything, but it's still there.
Yeah, it has to occupy some space, and it can't just. I mean, based on the quantum numbers, it has to occupy some orbital in some part of this atom.
The lone pairs are always SP2.
Yes, well, no, if, so like these, if, when you looked at HC triple bond N, this nitrogen is sp hybridized, so these lone pairs are in an sp hybridized orbital. Typically, the lone pairs are going to be in the same type of orbital that the atom is sp hybridized, or no, that the atom is hybridized in. So if the atom is an sp2 hybrid atom,
Yeah.
then the lone pairs are going to occupy an sp2 hybrid orbital.
Like the one that's SP3.
Mhm.
The lone pair.
Yeah.
Is SP3?
So the lone pair occupies an sp3 orbital. Yes. The atom nitrogen is like when we talk about hybridization, we're talking about the atom, we're not saying that these electrons are sp3 hybrid electrons. We're saying that this atom is sp3 hybridized, meaning that the electrons in its valence shell are going to be in sp3 hybridized orbitals. So each of these regions has to occupy an orbital, and it just so happens when you have sp3, they're all occupying an sp3 orbital. Yeah.
So all of like the lone pairs and the single bonds would occupy the same hybridization as like the main atom, except for if there's like a double bond or a triple bond.
Exactly.
Okay.
Exactly. Perfect.
Quick question, so for a triple bond, would the P be a P2 or would it be different?
Let's see, we have. Let's just draw the thing. So you're saying the P,
Because on the.
oh, I did that wrong. I feel like my friend.
The one we just did, it was what's it called? The pi bond with P, because it was just like one sigma bond and then a pi bond with a double bond. So for a triple bond would be like the pi bond would be a 2p or.
So the pi bonds, there's two pi bonds,
Yeah, there
but
was two.
they're each p orbitals, and technically for carbon, they are. I don't want to confuse you, but they are coming from the second energy p subshell, so two p orbitals.
So I guess we get the hybridization part. Do you think that they're gonna ask questions like question 12 on the exam? Or we're gonna have to see like that the pies are.
Yeah, what I've noticed is that his review is very close to like the type of questions he's gonna take from the exam. So this question 12 is definitely like, you'll probably see something like it on the exam. What part?
Why? P, where the answer to? P.
Because you, okay, remember how we said this is composed of a sigma bond and a pi bond. Pi bonds are composed of what kind of orbital? P. Think of, when you think of pi bonds, think of p orbitals. So therefore, for this bond to have that double bond, you need to have a p orbital bond, which is our pi bond.
Okay.
Our pi bond is composed of two p orbitals that are overlapping to make a pi bond, which is why it needs the p on nitrogen. I feel like the best way to show this is using orbitals instead of bonds.
I get the P's on pi, but I don't get why the H is the S.
Yeah.
It's H only bond with one thing, so it's only gonna have one single bond.
But then that example he showed us with we had like three H's about it. If I want those all S's, those were also S. Well, the H would be S, but like that's not the hybrid. The hybridization of H should be S. Oh, that's out in the middle.
Okay, so the best way to understand this is by, the best way to envision it is using literally what the orbitals look like. And saying, you're gonna be like, what the hell is he drawing? But this is literally what the orbitals look like. And we see that nitrogen has these three lobes right here. These are our sp2 hybrid orbitals. Okay. We can see that hydrogen has a circular orbital, that is our s orbital. Hydrogen is not hybridized, it has a single s orbital. So which is why we look at answer choice B, we have an S on hydrogen, okay? You can cross out, yeah, D. And anytime you see something that says SP, SP2, or SP3 for hydrogen, you can cross it out because hydrogen doesn't hybridize. Where were we? So everything in blue is a nitrogen sp2 orbital. Okay, so sp2. Everything in red is a nitrogen p orbital. And the way the p orbitals work is they're not a direct overlap. They have this weird interference pattern where they constructively interfere to form a bond. So because these are our p orbitals, this is why we have a bond, in this case, our double bond occurring between nitrogen and nitrogen, between their two p orbitals, which is why you have n equals p for that. And nitrogen is also using blue sp2 orbitals to bond with hydrogen and also to nitrogen, because we see that there's a double bond there, right? So nitrogen is using an sp2 hybrid orbital to bond to the other nitrogen. It's also using a p orbital to bond to the other nitrogen atom, which gives it that double bond that we've been talking about. Which is why nitrogen is using sp2 and P. Hydrogen is just using S. And we see that the lone pair over here occupies a blue sp2 hybridized orbital, which is why the lone pair on nitrogens occupy that blue sp2 orbital as in the androgens. Does it make more sense?
Yeah, that was a good one.
Okay, that was a good one.
Yeah, that was very good.
That's good. Is there any other things that y'all are like that were confusing? Anyone on Zoom, is there any things that were kind of confusing that you would like a mini lecture on? Yeah, yes, no, anything? Maybe any?
Oh.
Yeah.
Were these equation?
Can you go over question 6 on the exam? Can I see that? Sean? Or, I don't know if this is the one that I'm on. There's like 2. Alright, we're gonna go with, is this the one you thought?
Yeah, we're going to chapter 7 there is one in chapter 9, 11.
Gonna have both of them for right now?
Yeah.
Okay,
So, yeah.
all right, everyone. Let's settle down. Okay, let's see. So somebody asked, is it the question you were talking about? Person who asked? I didn't see the name, but whoever asked about question 6. Yes, okay, perfect. Nice. Let's crop this up a little bit. So it's asking for assign formal charges to all atoms in the resonance form for nitric acid. So we start by, the quickest way to do this is memorize some things. But if not, what's the formula for formal charge? Someone said the first part. You want to finish? Anyone else? So valence electrons that the atom typically has, right? This is found on the periodic table. So for example, oxygen would have how many valence electrons? Right, because it's in group 6. And then we subtract that from the electrons. Unbonded. I just like to say, I mean, it's a weird formula, but I just say by the electrons it has in that specific scenario. Like that's the way I say it in my head. So in this specific scenario, how many electrons does oxygen own on the very right? So we know for sure it has those 2. It has everything that it has a lone pair with, right? Because it owns that thing. And then it has half of this bond. So it has how many? 7. So electrons it owns is what we're going to go with. So it starts with 6 from the periodic table. You're always going to start with the periodic table. And then you're going to subtract of what it owns in this specific part. In this case, it has 7. So it would be 6 minus 7 equals -1. A quick way to identify that is every time oxygen has 1 bond, it has a -1 formal charge. Every time it has 3 bonds, it has a +1 formal charge. And every time it has 2 bonds, it's very happy. It has a positive charge of 0. So with that, I kind of gave you the answer for the other 2 oxygens. What are they?
0.
Or different thing, 0.
Well, they would be, yeah, they would both be 0. So they're both the same. It's because the quickest way is again to see, oh, it has 2 bonds, it has a formal charge of 0. But if you wanted to do it the other way, you would say, how many does it own? 1, 2, 3, 4, and it has half of the bond, so 5, 6. We know from the periodic table it should have how many? 6. It has 6 in this case, right? 6 right here. So 0. And you would do that process for both of these. And what about the nitrogen here? So nitrogen should have how many? It has on the periodic table how many electrons, valence electrons? 5, right? It can't be 6 because it's in a different group as oxygen. So it's in the group 5 right before oxygen. And then in this case, it has 1, 2, 3, 4. So 5 minus 4 equals +1. So therefore, this nitrogen will have a +1 formal charge. That's I actually drew that for y'all earlier, if you remember.
Whenever it's formal charge and it's asking like the bus structure, it's the one with the most zeros or the most negatives.
The most zeros. Because that means all the atoms are happy. But if you were to have a -1, you would want the negative charge on the most electronegative atom.
You also find it by doing those like bonds plus.
You keep that formula to yourself, okay?
Because somebody like that.
Valence electrons minus bonds, minus the electrons in the lone pair, sure.
It's like half the bonds, that's what you complicate.
Yeah.
Remember that formal charge rules, Trump on that rules.
Okay,
That's actually cool.
anything else from the,
The Lewis structure, like.
the one from class, which one did he do?
Like, if you're in the Lewis structure, you want the.
Yeah,
atoms to have a
did he do an
zero-
exam review in class?
Oh, no. Oh, or I believe.
Oh, y'all have a different.
Yeah, or she just posted. His
All right,
review.
are there any other concepts anyone wants to go over?
Like, so what's so wrong with that?
Oh, yeah, it was like really stuff.
Okay,
And then if we can, like, we go to later, like after. Yeah, I was like.
Polarity.
Yeah, like that. It's kind of. What word? It's not, it's confusing, it's just I feel like. I'm back. Our mom's explains. Yeah, that's it. So it's-
all right, this is a wavelength one. Is there going to be any questions about bond strength? Oh, bond length. Probably. I mean, it's definitely, yeah, single. So we can just go over that quick. Single, longest, weakest. I guess this is middle. Intermediate size.
But
Shortest. Nothing wrong with that. Also the strongest stuff. So, these are the intermediates, okay? So that's the way bond length you would do that. Okay, the wavelength of one of the spectral lines of helium is 492 nanometers. What is the energy of a photon with this wavelength? All right, there's really one equation that can be derived to another way, but there's 2 basic equations that explain that relate energy of a photon to its wavelength or its frequency. What is the one for frequency? That's what I said. I said there's an equation that relates energy of photon to either its wavelength or its frequency. What are the equations? So that's one of them. Planck's constant times the speed of light over lambda, and the other one is. Did you say?
E equals HV.
Yeah, so E equals H times V, but I don't like V because it makes no sense. I use F. And we're not going to grade you on whether you use HV or HF. I use HF. I've used it since high school chemistry. Yeah,
Remember if you remember about how many the responses on this?
I don't know. They change it every semester.
Is there one? Can I do a waiting for me? Since it's like
Problem.
a whole calculation, pretty much.
There's a lot of other calculations, but it'll probably be one of them, yeah.
Expect approximately 5. I think that's a decent number.
Yeah, you know how to do this one for sure.
Yeah.
Probably like a Rydberg equation. Maybe definitely a bond enthalpy, y'all remember the bonds broken minus bonds formed, reactions minus products.
What is it called?
All right, so
Straight.
Where do we find that?
I know. That's any kind of what-
all right, everyone. Which one should I be using for this problem?
The first one,
I agree. Why?
Because you have to wait.
Yeah, so they give us wavelength. So they give us 492 nanometers. So clearly that's a wavelength, and we should use the equation that incorporates wavelength in relation to energy. So we're gonna erase the second equation. So let's do a quick refresher of what Planck's constant is. What is Planck's constant? What are the units?
Or Jules.
It's joule seconds, and the quickest way to figure that out is E equals HF. If you solve for H, you get E over F equals H. Well, F is just units of 1/seconds. Energy is in units of joules. So H must be in units of joules times seconds. What is the speed of light?
3 times 10 to the 8.
All right, we're gonna, for this class, we go by 2.998 times 10 to the 8. All right, it's not a big difference. I mean, it's only a couple million, but for, yeah, okay. So for this class, you're gonna use that. It probably won't make your answer different by much, but I just use it, okay,
No,
just in case.
okay.
Now, all right, what is another thing you should be careful about when doing these problems?
When it says nanometers, you put it in meters.
Exactly, that's exactly what I was going for. So we know that the speed of light is in units of meters per second, so that means our wavelength must also be in meters in order for those units to cancel out. So 492 nanometers converts to how many meters?
Or four. To the power of eight.
Yeah, so there's 1 times 10 to the minus, or 10 to the 9th nanometers is 1 meter, which means that there's 400. We're dealing with 492 times 10 to the minus 9 meters. So if we just plug all that into this wonderful equation, that's gonna give you your 100 on the exam. It's 0.626 times 10 to the 4. Can someone do this on their calculator while I'm doing this? 998 times 10 to the 8 divided by 492 10 to the minus 9.
4.037 times 10 to the negative 9.
4.037.
4.03, or I get 4.04 times 10 to the negative 9.
Negative 19 what? Like seconds?
Sorry,
Joules, right?
just rules here.
Joules, yeah.
Then after that, you have to put proton, do the divide by other number or something.
No, not necessarily, because we're already assuming that when we talk about wavelength, we talk about the wavelength of a single photon. We can never talk about the wavelength of a bunch of photons.
Okay. But isn't there a scenario where you have to do that? What was the question?
There is, I think I have one in here. Let me. Oh, look at this element we created. So
Wait,
Yeah.
that was answered the other one?
what?
That was answered. That's answered.
Give me a second. I'm trying to find the other problem that is referring to. It's a good problem we can do.
If not, I can probably make one up real quick. Oh.
All right, so this is your problem.
Alright.
All right, so this is the type of problem you might be thinking about.
Yeah. First,
I mean, I don't think it is, but I think this is what you're talking about, where it's like the, what's it called? The ionization energy. Cesium is 575 kilojoules per mole. What is the wavelength?
Cesium. It would just say cesium.
Yeah, what is the wavelength?
Kennedy, what does that say?
Sure, okay. But it did not write as fast.
No, it's fine, you're gonna take much time. Okay,
Thank God for the other people.
just read it out to Kennedy.
All right, so the ionization energy of cesium is 575 kilojoules per mole. What is the wavelength of cesium? Well, that's where you'd find out.
So the ionization energy is like RT and then we're just.
Pretty much, yeah.
Oh, and the.
Yeah, because this is the scenario in which you have to use Avogadro's number. Why? Because they give you moles. If they give you moles, you can convert to like cesium atoms. And then from there, you can solve it out. I'll let you all do the fun part, calculate it out for a bit.
This is the one you divide. Yeah, no, can you like- Yes.
So,
The longest would say you go to MI.
Starts with it.
It's true, you can convert it down to stuff.
I'm probably very good at it.
Got it.
You gotta, it's gonna be like 20.
No, this part is-
Are we by a difference or what are we gonna do?
y'all have an answer?
Only on the-
first step, finding rules, and then the way to set that energy equal to
Convert it.
H over wavelength, and then when you put those in.
There's some way to get rid of the moles. We do that first,
Yeah.
and then you
Right.
can.
You do dividing by number.
Divide that over this number, and then that would get you kilojoules. Not like kilojoules,
Yes, the
I mean, it's-
One ball.
and that would be,
yeah.
and then you start, or you can like. What is it? Divide E by H and C.
Yeah.
So you're like,
So,
You want to show me the difference? I think we did before, like.
all right, let's show you on. So as some people in the class have stated, so first you need to get rid of the moles. So 575 kilojoules over 1 mole. And then you say that 1 mole, how do we get from moles to atoms? What number do you use? So 6 Avogadro's number, yeah, 6.022 times 10 to the 23rd. I'll say cesium atoms. And then we got that, so our units now are in kilojoules per cesium atoms, because the moles gets that. Then, as someone said, we convert the kilojoules into joules. So how do we do that? How many joules are in a kilojoule? Exactly 1,000, yeah, or 10,000 joules. So this is our E. So if we solve this out in our calculator, we will get. Y'all should get something like 9.55 times 10 to the negative 19 joules. Now, as somebody else stated, it's asking for wavelength. So we know that E equals HC over lambda. So now, to get lambda, all you have to do is take the HC and divide it by E. So if we do that, we will get, say, 6.626 times 10 to the negative 6.626.
What unit do you want?
Maybe
SIU.
Years. One sec.
241.
Yeah, they always.
Yeah, that's what you do. Minus the two vertical atom.
So once you do that calculation, what you'll get is 2.08 times 10 to the negative 7 meters.
Yeah.
You put things constant in the denominator.
Yeah, you.
Yeah. Or that's it, you
You would do,
remember by itself, you divide.
no, you would multiply by lambda and divide by E, right? Because if you divide by HC, you're left with E over HC equals 1 over your solid for 1.
Oh, yeah, yeah.
Or if you want to get, or you could do it that way, get 1 over lambda, then just do the reciprocal, but that's way too complicated.
Yeah, that's just complicated. It's complicated.
All right, so this is probably the thing you were talking about, where if it gives you kilojoules per mole, that's your key to the dominant.
For this is, tutoring. And the question is, if the wavelength of gamma radiation of cobalt 60 is 2.00 times 10 to the negative 12 meters.
Is it in this thing?
Energy of the photon. Of the photon is radiation. So now how we do this earlier? So we didn't divide in by.
I don't see where you would be.
It isn't in this thing.
Yeah, it's not. Oh, that's a star sheet.
Stars.
Stars.
This is almost like being here.
Oh my God. We said about.
You to the charging.
Yeah.
I know.
Because we know. Give us 1 second, everyone on Zoom.
It's not me, what do you do with that?
All right, 1 second.
No way.
There was a question of it. 1 second, Zoom people. All right, everyone. Party people. All right, this is the one that Rich is about to attack.
All right. Cobalt 60 is an artificial, I don't care. If the wavelength of gamma radiation is 2 times 10 to the minus 12, calculate the energy of a photon from this radiation. So it gives us wavelength. So what equation do we use? Yep. E equals HC over lambda. Now, our wavelength's in meters already, so do we need to do anything?
No.
So we can just plug it straight in, right? Yeah, so that's exactly what we're gonna do. So to get our energy, 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8. And this is all gonna be over 2 times 10 to the minus 12. Now, if we solve out this great monstrosity and put it in our calculator. We know that. What?
That's no.
We will get 9.93 times 10 to the negative 14.
Better than nothing. What did or?
You can do number two. On the sheet. The one that says 7 and 8 on.
7, according to the Harvard Rayburn equation.
Yeah.
All right.
You got that.
Oh, Dylan, how do you take a picture on this one?
Okay, that's what I got.
Press the plus.
Like, you need to divide.
See, this is what I'm.
Cameron.
She doesn't know. That she doesn't. Yeah, we also discussion because I'm in the way.
So each.
So long, so.
I got that, but then after you go back, it was like, you're not done. So it's like, you need to divide.
If you ever violation. What did
Alright.
Yeah.
Oh.
To be a TA, you have to get a B. To be an SI, you have to have an
Huh?
A, right? Don't you have an A to be an SI?
Other way around.
Other way around.
Yeah.
A to B to a TA.
Oh, wait,
I'm split.
anyways.
That you like wrote out, was the answer 2.08 10 to the negative 7?
Sounds about right, yeah.
Okay.
2.0. You should get something times 10 to the negative 7. All right, we got a request to do number 2, so I'm gonna jump into that. According to the Balmer-Rydberg equation, electromagnetic radiation with a wavelength of 46.1 nanometers will be absorbed when an electron undergoes each of the following transitions. All right, first and foremost, it says absorb, right? So are we going from a lower number to a higher number, or higher number to a lower? Low to high. So we can cross out B. We can cross out. What did I do?
Bro, what? Where's the? No, this would be.
Okay, moving on. According, electromagnetic radiation with a wavelength of that will be absorbed.
I'm so glad I don't have green.
So absorbed is lower to higher numbers, so you cross out options B and D. So then we're left with A and C.
No,
So 46.1 nanometers, what region is that in? Like the visible light, ultraviolets? Yeah.
we actually need to know that, like, green.
No, like around, like, no, like not the exact numbers, but like no around where stuff is.
Okay.
Yeah, so it's like 400 to like 700 is the visible light region. You know, like, all right, anyway, 400 to 700 is the visible light region. So if it's 486, is that a wavelength with really high energy or really low?
You said visible light.
Yeah,
It's gonna be lower.
low energy, but it's a small wavelength.
Well, small wave, higher. Lower.
Yeah, but this is small wave. So it should have a pretty high. Remember, it's 400 to 700. So anything in like the 400 region, that's like purple. And purple has a higher energy than red. So if it's like 486, then that's a smaller wavelength in this range. So it would have a higher energy. That's what would lead me to C beside instead of A. Because A is only one energy transition, whereas C is 2 energy transitions. And for this, since we know it's higher in energy, I'm gonna go with C. Seven.
Is that M? Is that M?
Yeah, so then.
Because we, like, the next year, like, we did a whole family.
No, you don't need to do math equations if you understand like what's it called?
Because
The.
It's a higher difference.
Because I know that 486.1 is a high energy photon. So if it's a high energy, it'll probably jump between a larger transistor.
Susanna asked you, Rich, what does the end mean?
The M is just like your initial point. Like, it could be like, I don't know, they use M and N for some reason, but M is just like your initial point, and then like N is your final point.
Yeah.
And then M is her initial N.
All right, any other requests?
Yeah. Yeah.
Yeah. Unfortunately, we have a meeting. About the exam tomorrow. To let you know the hearing. Thank you. I'm always on your question. Yes.
Oh, it's everybody.
But if you ever review again.
That's one. That one is supposed to be.
I'm not. I don't know.